tautologies,
and fallacies.
we are Yao Ron. Tautologies.
Fallacies. And today,
we are going to discuss about tautologies.
and fallacies.
Now, let's head to the classroom. Where's your ID? Where's yours? Where's your ID? You all owe me something tomorrow if you don't bring your IDs. Then, that means no plus points.
So, if we wear our ID, sir,
Aba, then that means you get plus points. So if you bring your ID, you get plus points. And if you don't bring your ID, well, obviously you don't get plus points. This can be expressed as a tautology in logical terms. Let P, you get plus points. This statement can be expressed as P or not P or P or not P. Either you get plus points or you don't.
what? I don't get tautology.
Let's discuss this. To understand why this table is the way it is, consider the following example. The statement will be true if I keep my promise and false if I don't. Suppose it's true that you bring your ID and it's true that I give you plus points since I kept my promise. The implication is true. This corresponds to the first line in the table. Suppose it's true that you bring your ID but it's false that I give you plus points. Since I didn't keep my promise, the implication is false. This corresponds to the second line of the table. What if it's false? Meaning you didn't bring your ID. Whether or not I give you plus points, I haven't broken my promise yet. Thus, the implication can't be false, so it must be true. This explains the last two lines of the table. P and Q are equivalent. So, the double implication is true if P and Q are both true, or if P and Q are both false. Otherwise, the double implication is false.
P or not P. This expression states that either P is true or false. This is always true because one of these must always be the case. To have a deeper understanding about this expression, I have here a situation. You are considering whether or not you will buy a luxury item. Let P, you decide to buy the luxury item, or not P, you decide not to buy the luxury item. To explain this, the first row shows that P is true, which means that if you decide to buy the luxury item, P is true. Then P or not P is true because P holds regardless of whatever P, not P is false. The second row shows that P is false, which means that if you decide not to buy the luxury item, not P is true, then P or not P is still true because not P holds. Conclusion: this is a tautology because no matter what choice you make, whether you buy a luxury item or not, one of the two conditions, either P or not P, must always be true. P and Q implies to P. This expression states if P is true, then P or Q is true. Since P or Q will always be true, if P is true, this is always true. To have a deeper understanding about this expression, I have here a situation. Imagine you are attending a meeting at work, and there's a rule that you can only attend if you're both invited by your boss, which is P, and you have completed the requirement preparation work, which is Q. P, you're invited to the meeting, and Q, you have completed the required preparation for work. If you are invited, P, you have completed the preparation, Q, then it logically follows that you are invited to the meeting, which is P. If both conditions P and Q are true, you're invited and you've done the required preparation, then you're certainly invited to the meeting. The first row shows that both P and Q are true. If you are invited to P and you have completed the preparation Q, then the expression P and Q implies that P holds true. You are invited, so the implication is true. The second row states that you are invited but have not completed the preparation, even though you have not done the preparation. Q is false. The implication still holds true because the premise P and Q is false. In logic, when the premise of an implication is false, the implication is considered true regardless of the conclusion. The third row shows that P is false and Q is true. You are not invited. P is false. So the statement P and Q is false. And the implication still holds true by the same logic in row 2. The fourth row shows that both P and Q are false. In this case, you are neither invited nor prepared. Conclusion. This tautology makes sense in everyday terms. If both conditions are met, invitation and preparation, then it is guaranteed that you are invited to the meeting. The logical implication holds true in all cases because if the premise P and Q is true, P being invited is also true. So P implies to Q, or Q implies to P. This expression says either if P is true, then Q is true, or if Q is true, then P is true. This expression asserts that in any situation, one of these two conditions will hold. To understand more about this expression, I have here another situation. You are trying to make plans with a friend whether to go freediving. You and your friend have two possible conditions for going freediving, which in P, you are free to go freediving, and for Q, your friend is free to go freediving today. This expression, P implies to Q or Q implies to P, would apply to the situation as follows. Whereas P implies to Q means if you are free, then your friend is free. And for Q implies to P means if your friend is free, then you are free. The first row shows that both P and Q are true. If you are free and your friends are also free, both P implies to Q and Q implies to P are true. The disjunction P implies to Q or Q implies to P is true. At least one part of the statement holds. The second row shows that P is true and Q is false. Since P is true and Q is false, P implies that Q is false. But Q implies that P is true. Because if your friend is not free, then you being free means the statement holds. Thus, the disjunction is true. The third row shows that you are not free, but your friend is. The fourth row shows that both P and Q are false. If neither you nor your friend is free, both P implies to Q and Q implies to P are true, since both implications are trivially true when the antecedent is false. Thus, the disjunction is true. Conclusion. If your friend is free, then you must be free. So, no matter the situation, one of these conditions will always be true, making P implies to Q or Q implies to P a tautology. P or P and Q. This expression represents a tautology because it is always true. This statement can be understood as either P is true or both P and Q are true. To understand more about this expression, I have here a situation. Imagine you are deciding when to go for a walk, whereas P, you decide to go for a walk, and for Q, the weather is nice. The expression P or P and Q says either you'll go for a walk or both of you will go for a walk and the weather is nice. The first row states that you go for a walk and the weather is nice. If you desire to go for a walk, P is true, and the weather is nice, Q is true. Then both P and Q are true. So the disjunction is true. The second row states that you go for a walk, but the weather is not nice. Even though the weather is not nice, Q is false, as long as P is true. You decide to go for a walk. The disjunction is true because P holds. The third row states that you don't go for a walk, but the weather is nice. Since P is false, you decide not to go for a walk. The second part, P and Q, is false. The disjunction will be false because both parts of the disjunction are false. The fourth row states that you don't go for a walk and the weather is not nice. In this case, both P and Q are false. So, the disjunction is false. Conclusion. This is a tautology because the statement P or P and Q is always true when P is true.
Fallacies. A fallacy refers to a reasoning error or a mistake in logic that leads to a false or invalid conclusion. Fallacies often arise from incorrect assumptions, misuse of mathematical rules, or faulty logic, and they can undermine the validity of mathematical proofs or arguments. So here we have the 5 types of fallacies. First, we have the fallacy of affirming the conclusion. It is a logical error that occurs in deductive reasoning. It involves incorrectly assuming that because the conclusion of an argument is true, the premises must also be true. This fallacy happens when someone makes the mistake or reasoning backwards from the conclusion to the premise, which is what happens in conditional statements. So, in a valid conditional argument, the form is if A then B. So, if A is true, then B is also true. So, B is true. Therefore, A is also true. This is invalid reasoning and a fallacy because just because the conclusion of B is true, it does not necessarily imply that the premise of A must be true. There could be other reasons for B to be true. So, for example, a number is divisible by 4, then it is divisible by 2. This number is divisible by 2. This number must be divisible by 4. So, in conclusion, this reasoning is incorrect because there are numbers like 6 that are divisible by 2 but not by 4. Hence, the conclusion does not logically follow from the premise. A implies B, and B is true, but that does not necessarily mean that A is true. Number 2. Fallacy of denying hypothesis. When someone makes the mistake of assuming that if a hypothesis in a conditional statement is wrong, then the conclusion must also be false. They are committing this fallacy. Stated differently, it entails dismissing the hypothesis and mistakenly believing that the conclusion is false, even if it may still be true. So, a conditional statement in logic is often expressed as if P, then Q. Denying the hypothesis of P does not necessarily mean that Q is false. For example, if a number is divisible by 6, then it is divisible by 2. So here, the hypothesis is the number is divisible by 6. And the conclusion is the number is divisible by 2. So the statement can be written as A to B, which means if A is true, then B also must be true. It is a fallacious reasoning. Someone might say, since the number is not divisible by 6, it must not be divisible by 2. So this is incorrect because the number could still be divisible by 2 even if it's not 6. For example, 4 is divisible by 2 but not by 6. Number 3. Circular reasoning. This occurs when a mathematical argument or logical reasoning process relies on the conclusion being true in order to prove that conclusion, effectively creating a loop that doesn't provide any valid support. In this fallacy, the argument doesn't introduce any new information but just restates the conclusion in a different way. So for example, we know that the sum of the interior angles of a triangle is 180 degrees because that is what the sum theorem states. Premise: the angle sum theorem states that the sum of the interior angle of a triangle is 180 degree. So therefore, the sum of the interior angle of a triangle is 180 degrees. So this is circular because it relies on the theorem's conclusion that the sum of angle is 180 degrees to prove the theorem itself instead of independently justifying the statement. So number 4, false analogy. This occurs when two things are compared based on similar properties, but the comparison is misleading because the things being compared are not actually similar in the relevant aspect. So for example, just like you can divide a number by another number, you should be able to divide a square by another square and get a new square. Sounds logical because you're comparing division of numbers to division of shapes. This is a false analogy because the division of numbers works differently than the idea of dividing squares. When you divide 6 by 2, you get a number 3. So if you divide a square into smaller squares, the new shape is not necessarily a square itself. For example, if you cut a square in half, you get 2 rectangles, not 2 smaller squares. So in conclusion, the analogy is misleading because dividing shapes like squares doesn't work the same way as dividing numbers. And the properties of division don't apply in the same way to geometric objects. So number 5, reductio ad absurdum. Reductio ad absurdum is often called proof by contradiction. It is a logical method used to prove the truth of a statement. It involves assuming the opposite of the statement and showing that this assumption leads to a contradiction. So for example, prove that there is no smallest positive integer. These are the steps for reductio ad absurdum. Number 1, assume the opposite. Suppose there is a smallest positive integer denoted by n. Number 2, premise. A smaller positive integer cannot exist because of n. It is the smallest by definition. Number 3, analyze. Consider n minus 1 since n is positive. N minus 1 is also positive and smaller than n. Number 4, contradiction. This contradicts the assumption that n is the smallest positive integer as n minus 1 is smaller. In conclusion, the assumption that a smallest positive integer exists must be false. Thus, no smallest positive integer exists. So this reasoning demonstrates that for any positive integer n, you can always find a smaller positive integer by subtracting 1. Therefore, the assumption that a smallest positive integer exists leads to an impossibility. So, that's the wrap up for our 5 types of fallacies. Thank you for listening.